So hello everyone. Right now we are nearing to the test and we still haven't solved the binary search trees. So let's get into it. And before we move forward with the binary search trees.c file, we do need to check out the header file that we have made. A few disclaimers before we get into that. So in this particular video, we shall be going over the problem to understand them as well as to construct the header files that we need for our binary search tree application or implementation. Okay, so everything should be fine. Now let's get into it. First, the thing is that we have a lot of problems here, but if you see that we don't have a particular problem that states or narrates the issue with basically building a binary search tree. So in the .h file, as you can see, we have first defined the .h file naming scheme, as well as so that we don't basically include multiple things, multiple libraries again and again. And then we have included the utils.h that we have built in the previous video, probably the first video of this channel. You can check it out. Now after that, we have done basically the prototyping of each and every problem, but before that we have made this, which is a BT node insert into the BST. BST stands for binary search tree, and there we are taking the root node as well as we are taking the data input to be input by the user, and we are returning the node of the tree. So as you can see, these doc strings, okay, one disclaimer is these doc strings are currently being generated by probably WinSub or Codium. I have kind of mashed them together, so I don't even know which one is generating these doc strings at this point. But yeah, these are basically to help out let's say reader or maybe the next programmer in this session to check out or understand which code is doing which for what is being done by what. Now the first problem basically asks us to check if a binary tree if a binary tree is a binary search tree. So we are basically creating two functions. One is the main isBST function and another is a boolean function. Now this boolean function is actually the main function, and this isBST is basically our wrapper for this function. Now this function basically checks if a given binary tree is a BST, and it takes the root as well as the two parameters. These are in minimum and the maximum, which we are going to get from the limits.h for int minimum and int maximum. And you do know how this int minimum and maximum works. Basically in a system, in a 64-bit system, you have 4 bytes allocated to integers. Means you have 4 into 8, that's 32 bits allocated to integer system, divided by 2 because you need positive and negative. So you want allocate 1 bit for your sign bit. Okay, then you have 2 to the power 31, so that gives you the negative sign as negative 2 to the power 31 and the positive int max as 2 to the power 31 minus 1. Minus 1 means like whatever the value of 2 to the power 31 is, subtract 1 from that value and you get the int maximum. Now after that, we are now basically just checking and everything, and this is the wrapper. With that, we can move on to the problem number 2, which is to get the elements in the range k1 and k2. Let's see the question that asks, basically given a root of a binary tree having integers as the information part and 2 integers k1 and k2 as input, write a function to get all the elements in the range k1 and k2 in the tree. So how do we do that? The implementation will be discussed in the later videos, but here we are basically having the structure here. Here is the problem 2. So here in the problem 2, we can see that we have got like, wait, where is it? Yeah, sorry, even I was just confusing. So basically it prints the range and it takes the root node, the k1 and k2 integers. Next, the problem 3. Oh, did I do something? Oh, sorry. Okay, so next we have in the problem 3, given the root of a binary search trees t1 and t2, check whether the two trees contain the same information or not. The structure of T1 and T2 can be different or the same. So basically we need to check if both of them have the same information or the data path is the same or not. So for that, we can just have the root and this basically we need to traverse now. So for this we need to have an array to store the traversal order, or basically whatever currently here we are using in order traversal, and with that we are just storing. You will see the implementation, the root, the array, and the index, how we are doing that. We also need to count the number of nodes, basically to save us some time. Suppose a tree has 5 nodes and the other has 6 nodes, of course they are not the same, so with that we can save up some time. And we have a checker which basically checks if they have the same info or not, taking 2 nodes and do the checking for it. Okay, this is just to save time, for a not time, basically it's just to save a few lines or make the program more readable when you don't have that if this node equal to this node and then return this whole path. You don't have to write it again and again, because this is a repeating part of the programming structure. Next, the binary tree is balanced if for every node in the tree the heights of the left and the right children differ by at most 1. So you know this is a balancing factor, that the height of the left subtree minus the height of the right subtree without the mod. This is basically the logic for your AVL tree. In other words, if we define the balancing factor of any binary tree, so yeah, these are the AVL tree. Given the node of a tree, write a function to check whether it is height balanced or not, basically checking if this is a valid AVL tree. AVL stands for the people who made the first data structure. Let me just check the recording. Yeah, it's recording, and let's go. And so for the fourth question, we just have 2 main functions for it. Is the height balance? This is basically the wrapper for this one. And basically you just traverse and do the checking of the height, and this basically checks the wrapper. So this not checks, this is the wrapper. So this is the structure that we are following. Nothing more to say, it's very simple. Now next, given the root of a binary search tree and 2 integers a and b, remove all the elements which are outside the range. So remember the second question, that we have to return the integers in the binary BST that are falling inside the k1 and k2. Now here we are basically having outside the range of k1 and k2, and not here a and b, and we need to basically remove all those elements. And this is a challenge problem, removing the elements outside the range. Modify the existing binary search tree containing all the elements inside the range. Okay, now let's go here. This is the part. Basically remove the elements outside the range, and you can just have the simple function that is your remove outside range bt node, and you just return the modified tree after this. Okay, next, given the root of a binary search tree, write a program to make another tree that would contain all the values values which are the sum of the present value in the tree, the values in the left subtree, and the values in the right subtree. Following is a sample input in the left and the right. So probably this is the one that he's talking about. And so where is it? Yeah. So if you just go here, I think this, yeah, this is the one. So it's 15. Now then, as you can see, if you just sum it all up, so 15 means basically you have to sum all of them, and you basically get all the sums, so 129. Then as you can see here, if you sum this part up and you get the 90, you sum this part out, you get 20. I think this is a shorter example to not 24. That is basically your, what is this, 2 plus 1, that's 3, 10, 4 is 14, and 14 plus 10 is 24. So here you can see it is 24. So that's the logic behind this. Now we have to implement it with the following structure that we have thought about. So where is it? Yeah, create the sum tree values. Basically you just take the root node and you traverse and then add the sum and do it like that. And basically this is the function, and then this is the node, like other function that basically creates the sum tree and returns the bt node. And this one particularly calculates the sum of all the values in a tree and the root of the tree, and it returns the sum of the all values. Okay, so suppose you pass a root node, so maybe this node, say 24, I pass it, not 24, sorry, 10 I pass it, then this one will return the summation value, so it will return the 24, and this gets updated in this particular function. Now after that we have question number which one did we just do? Question 6. Yeah, 7. Given the root, yeah, 7 it is. Yeah. Convert the binary, basically given a binary tree, make a binary search tree with the value stored in the binary tree. So this is basically you convert one tree to the BST. I think we can actually see it in action in the later video part. So that's there. Next, for that we have given the root of a binary search tree, make a sorted doubly linked list with nodes. Think of the traversal technique that gives a sorted sequence from a binary search tree. Okay, that was just a hint. So if we go to the problem number 8, for this we were really required to make 3 different functions, basically from print the dynamic doubly linked list, that void function. Then we created the node function that returns the now converted binary tree. And finally we have the void that does the main heavy lifting for us. This is a wrapper and this is the basically the printing statement. So next we have given the root of a binary search tree t, output the sum of the values stored in the nodes of the binary search tree. So it is very similar to what we did in this one, question number 6. Now, some of the values in the binary search tree, and basically in the implementation we will see, because here I'm just showing you the header files, and this is a simple header file that returns the what do you call this, sum of all the node values. Now, next after that we have question number 10. Given the root of a binary search tree and an integer m as input, modify the tree such that all the elements in the tree having the value less than the given node or integer gets incremented by 5, and all the elements in the tree having values greater than m gets decremented by 5. Basically you are modifying the tree. Basically you go to each and every node, check if it is greater than equal to, and then you just modify, and it's a very simple function, so nothing much more to do. But the issue will come because suppose there are this is a binary search tree, means the structure, that is the left and right, the left being lower than the root node and the right being greater than the root node, needs to be followed. And basically each and every part after you increment or decrement, you check if it is still a valid thing, means the whole triangle structure is valid. If it is not, then you have to change the triangle structure, then again you do it. So that's why there needs to be a checker for this. Okay, in the logic you will just see. And next what we have is the 11th question. Given the root of a binary search tree and a integer value m as input, find the mth largest element in the binary search tree. So mth largest input basically means the so suppose I have a tree like this here, and if I want to find the mth, means say it is 2 or 3 or maybe 1 means the largest and mth means the second largest and something like that. So not that's the thing how you do it. So you take the m, you also have a count, you have to get the results as well, and this is to find the largest. Basically this is the wrapper function for this one, and this is the main function that does the all heavy lifting. It basically, if you just go the parameter, it takes the root of the binary tree, and also m being the rank, that means 1 is the largest, second for 2 for the second largest, and all this. Then pointed to the counter tracking visited nodes in reverse order. I don't know, this was generated by this guy. It made it too complicated, I think. Oh, I was reading it visibility, sorry. Visited node, yeah. So basically, suppose you have a node and you want to count the, let's say suppose I go to some, let's say I do one kind of traversal. Say I do pre-order traversal here, and here. And then after this, you go here, then you go back to this part. So that's how you generally go along traversing a tree, but you do need to keep a count on how many nodes you are actually counting or visiting. Okay, the new node that you are visiting, and that count actually helps us out in finding out the largest or the mth largest value. Now after that, what do we have in the problem number 12? Given this file, make a binary tree. So yeah, This was the done in class. So where is it? Yeah, this is the word, like basically you do need to have this frequency and the length parameters in the like new structure. That's the frequency node. And this frequency node, okay, this was done in class, so probably I won't be getting into much details, but this is the base structure that we shall be following for the upcoming videos for solving this binary search tree assignment number 2. So that's all for this video, and see you in the next video.